Welcome to Module 9. In this module, we'll be taking a look at coasts, shorelines, and the features that we associate with the coastlines of all the world's oceans. In this module, we'll be taking a look at coastlines and sea level. We'll take a look at what coastal zones we are, how we can break up the coast into specific areas. We'll take a quick look at sediment transport, especially in terms of how sediment is transported and deposited on the beach. We'll look at features of both erosional coastlines and depositional coastlines. Take a look at the concept of coastal cells. I'll talk a little bit about submergent versus emergent coastlines. This has to deal with sea level. And finally finish off by taking a look at coastal erosion. Knowing what happens along a coastline is important if you consider the fact that 1/2 to 2/3 of the world's population lives in coastal areas. Here you have a picture of the harbour area of Sydney, Australia, and you can see just how closely related the city is, the suburbs, with the ocean. This is also important when we look in the fact that we see sea levels rising globally. We consider that just yesterday news reports were put out that there's been unprecedented melting of the Greenland ice cap, which has led to at least a 0.5 millimeter rise in sea level very recently. So looking at what happens along coastlines, because we have such a great amount, or we have a large population base living along coastlines, many of the world's major cities are located on coastlines, is important. So we'll jump right in and take a look at coastlines and sea level. And if we look at coastlines over geological time, we see that the location, the position of coastlines isn't static, but it's something that changes. Times in the past, coastlines have been much lower, sea levels been much lower, therefore the coastline extends much further onto the continental shelf. And in other times in the geological past, what we've seen is coastlines, or the present, or the sea level is much higher. So this little diagram here in this particular slide right here gives you an example of where coastlines lay at different times within the last 20,000 years. We see that the highest shoreline, this is the old shoreline we see that's up above the present shoreline, that was probably about 125,000 years ago. We see that up to about 20,000 years ago, 18,000 to 20,000 years ago, we saw sea level much lower than it is at the present day, at least 120 meters lower. Why is that? Well, if we look back in time, around 18,000 years ago to 12,000 years ago, what did we see? We saw that the Earth was in the midst of a global ice age. So all water in the liquid form was tied up in ice, and this caused sea levels to drop. In fact, if you go out on the present-day continental shelves, you still find evidence of human occupation in these shelf-full areas when sea level was much lower. So it isn't a given fact that over time the position of coastlines has changed. This does occur, and it occurs naturally. Before we get too much into human-induced naturally occurring sea level change, once again, this is a natural process. What's of concern is that human activity seems to be accelerating this process in the present day. So obviously, if sea level changes, it's going to affect the position of both what we consider the coast and the shore. And we'll talk about those two terms in a couple of minutes. We see that the shoreline and coastline positions change in response to sea level changes. The important thing here to remember, though, is it might not only be a rise or fall in water levels, it could also be an uplift or subsidence of the land, so vertical land movements. What could happen is we might have an episode of mountain building, so the land becomes uplifted. Sea level appears to be falling relative to the uplifting of the land, or the land could be sinking and sea level appears to be rising relative to land. So you got to remember that it can be both rising or falling of water or actual vertical movements of the land. We see that these positions are controlled by a number of factors. These factors can be global, or what's known as eustatic controls, or very local and regional controls. And we'll look at some of these different controls over the next number of slides. The final thing we see here on this map, we see the position of the modern day coastline shown in sort of a limey green. Peak glacial, so this is when all the ice or all of the liquid water is tied up in ice sheets covering the continents. That's outlined by sort of that pale teal blue. We see that it extends much further out past what the present day shoreline is. And then we see what the shorelines look like in peak interglacial. And interglacial refers to that period of time when all ice on Earth has melted and we're just left with liquid ice. Or not, sorry, liquid ice, but liquid water. So continue on in the themes that are talked about in the previous slide. What causes rises or falls in sea level? Well, a rise, obviously melting ice. And this is something that's dominating the news, especially in the last couple of days. We're looking at the end of July, early August of 2019 right now. So the last ice age, roughly from about 70,000 to 10,000 years ago. Here we saw ice sheets covering almost all of Canada. These ice sheets were thick, about 3 to 4 kilometers thick of ice sheets. And as I've said already, we see that sea level is lowered by 120 meters. The opposite, you melt all that ice, you're going to cause a rise in sea level, and quite a significant rise in sea level. Here is a hypothetical model of what would happen in terms of the modern day coastlines if all ice melts. So if we melt all the ice that forms part of the Greenland ice sheet, all the ice that melts the Antarctic ice sheet, and then any other ice we have present on the planet. And you can see that the belief is, and this is estimates, I've actually seen some higher estimates lately, but it would raise sea levels up to at least 6, or it could raise potentially sea levels up to a height of 66 meters. So we'll see major cities like Miami, the whole entire Florida panhandle completely disappears. But like New Orleans, Houston, Norfolk, New York, even Washington, D.C., Boston, all are going to experience massive coastal flooding. And these cities, in fact, might become unlivable. So you can see how this simple thing of melting as ice can really completely reshape the position and location of coastlines. What else can change the position of coastlines? Well, basically you change the volume of the ocean's container. So imagine it like this. You decide to go have a bath, you fill the bathtub up almost to the brim with water, and then you get into the bathtub. What happens? The water flows over the edge of the bathtub. You've added more material, more mass into sort of that container, that bathtub that's holding the water. That changes the volume. And there's a couple of ways that we can do this. We can have increases in seafloor spreading. So if we look at geological time, throughout geological time, there's episodes or periods when the amount of material, new oceanic crust that's being produced at the seafloor mid-ocean ridge is much greater than other times. We increase that seafloor spreading rate. We're going to be putting more material into that ocean basin. That's going to result in a rise in sea level. We can also have periods where we have very rapid erosion into the ocean. So cliffs, anything along the side of a coastline, erodes into the ocean. Once again, we're introducing new material into the ocean. This can have the effect of raising sea level as well. These, just like the previous one of melting ice, will cause quite often global sea level rise. A third global factor that will cause a rise in sea level is global warming, so variations in water temperature. What we see is as water warms up, that water molecule expands, seawater expands, occupies more space, and that's going to cause a rise in sea level. So not only is this global sea level rise can be drawn by global warming, causes more melting, which results in the rise in sea level, but then we also make those water molecules larger and even further increase that sea level rise. And this little graph on here just shows you an example of expected sea level rise due to thermal expansion as temperatures increase. The next two factors that we're going to look at that play a role in sea level rise are more regional or local than global. And one of these is tectonic motions and isostatic adjustments. So the Earth is constantly in motion. And one of the things that can cause the Earth to be in motion other than tectonic activity is isostatic adjustment. And this is what we're going to take a look at here. Imagine that once again, we're looking back at the ice age and you're ground and you have 3 to 4 kilometer thick sheet of ice on top of you. That's a lot of weight. What's going to happen is it's going to slightly depress the crust. So the crust starts to depress. Then when that ice is removed, what happens is the land is going to start to rebound. It's going to start to move back up. And this is called something referred to as isostatic adjustment or crustal rebound. So what can happen in this case then is that the land is actually rising up and it's appearing to rise relative to the sea level. So the sea level might be remaining static, but it'll appear to be falling as that coastal rebound occurs. So the land moves relative to sea level. Tectonic effects as well, tectonic motions. If we create a mountain, if we have a hot spot that creates a volcano in the ocean, or we have a volcanic island created near a mid-ocean ridge spreading center, that's going to make it seem as the land is rising relative to sea level. Other things, subsidence, once again, sinks the land down, and then the land seems to be sinking and sea level appears to be rising. So that's the one thing to keep in mind of all of these things, is that are we looking at actual sea level rise, or are we looking at motion of the land in an upward vertical motion or a downward vertical motion? Sometimes we could have both. We could have the land rising vertically as well as sea level rising vertically. And then it's a case of which is going at a faster rate, the sea level rise or the rise of land, the uplift of land. And then finally, we get very localized, very temporary rises in sea level. These aren't long-term. The other four factors we've talked about can produce or will produce long-term changes in sea level. This is when we have storm surge activity, strong winds, currents that basically push water up onto the shoreline, cause some periodic episodic flooding, and then the water levels return back down after that. So we get sometimes these very localized changes in sea level. A lot of these are related to either the weather or the climate. Now that we've talked about sea level change and some of the factors behind sea level rise or sea level fall, let's take a look at the actual coastal area itself. And we can divide the coastal area into sort of two broad zones. One of the zones we see right here, it's the shore. This is where the zone where the ocean meets the land. So it's that very, very, not very wide interface where the water runs up into shore. You can see the little buoy there standing right along the shoreline. Coast, on the other hand, is a much larger zone and is affected by all processes that occur along the shore. We'll see an example of the extent of the coastal zone in the next slide. Here we have a picture of the coast. The coast is the zone that extends inland as far as coastal processes reach. So as far as the highest storm waves might reach, storm waves during a high tide or a high spring tide. So it's all this environment that is immediately affected by marine processes. It extends a little ways offshore into something that we call the nearshore environment. We'll take a look at what that is in a few seconds. And then all the way up to, as far as I said, as maybe a tidal creek reaches in, as far as the tide water goes in, as the tide comes in, all of that area comprises the coastline. So it's much, much more extensive than the shore is. So let's move back to that part or area adjacent to the water. We can divide this up into 3 or 4 main parts. We have offshore, usually this is below low tide level. We have the offshore area or the nearshore area. Offshore is usually in deeper water. Nearshore means, I usually describe it as water that you can wade in or is just over your head when you get into it. This is followed by the foreshore. We have the shoreline there that's sort of outlined in that pink line. That's going to change depending on where the water position is. So high tide, the shoreline is going to move much further up that beach there. Low tide, that shoreline is going to shift closer to the deeper part of the ocean. And then finally, we have the backshore. Other ways to define these: backshore above high tide line, only covered by water during storms. The foreshore, portion of the beach or the shoreline here exposed at low tide but covered during high tide. So some of these people are walking definitely on the foreshore area. The near shore, never exposed out from the low tide line to where breakers form during low tide. And you can kind of see some breakers in the distance there, so that would denote the furthest extent of the near shore zone moving offshore. And then the offshore zone, waves never affect the bottom. We've talked about how waves affect the bottom in a previous lecture. So let's take a look at some distinctive features of the foreshore. And the first thing we'll take a look at is the beach face. The beach face is sort of this wet sloping surface that extends from something that we call the berm all the way down to the shoreline at that time. So remember, the shoreline is going to depend, or the position of the shoreline will depend on where the tide is at any given time. So it's that whole wide area outlined in yellow there. We find that this is usually a very sloped portion of the beach. Typically not steep, especially in the summertime, shallow sloping. It might become a little more steeper sloping in the wintertime. We'll talk about that in a little bit. And this is where we see a lot of activity going on. This is where we're going to have that swash and backwash as waves come in and waves go out. It tends to be finer grain sediment, but we can see coarser grain sediment as well along the beach face. Before we discuss what's happening in this picture, what this picture is showing, just a reminder, when I talk about something being finer grained, it means that it has smaller sized particles. When I talk about something being coarser grained, it has larger sized particles. So here we're taking a look at a feature called the berm. And the berm sort of extends from the foreshore. It sometimes may be part of the foreshore. It can sometimes be some part of the backshore. It really depends where it ends up. The berm is this dry, so instead of the beach face, which is wet, it's the dry, gently sloping, even though I have seen times where it's much steeper sloping. We'll look at that in the next slide. Slightly elevated margin of the beach, sort of that landward margin of the beach. It'll form above high tide by wave action. So it marks the highest point of the tide, the previous high tide episode. And that berm is actually can shift position day after day after day. It can be made of very coarse-grained rock. So here we see it pointing at coarse-grained rock. It can also be made up of finer grained material. We'll see an example of that in the next slide. Here we have another picture of a berm on a much sandier beach. We see that the berm here has a little bit steeper slope. The reason why is you're dealing with finer grain sediment here. Finer grain sediment, and typically this should be dry, but if it's a little wet, is going to be able to be a lot more stable at a steeper slope than looser, coarser grain material. So here's the berm once again. We have the beach face. You can see there it's the wet part of the beach. And then we stand up into the backshore environment. Sometimes it'll be a cliff. Here we actually see that the backshore environment consists of a series of sand dunes. Not only do we sometimes see dunes instead of cliffs, rocky cliffs as part of the backshore environment, but we also can see a few features offshore in the nearshore environment. And this is something called a longshore trough and a longshore bar. So remember, this is a very active environment. We have waves moving in and out, running up onto shore, running off the shore. And what these waves can do is transport sediment. What will happen sometimes is the sediment gets picked up by waves washing up onto the shoreline, up onto the beach. The sediment, typically finer grain sands, will be moved off into deeper water where it will be deposited and form longshore bars. And if you've ever gone wading, especially in an ocean setting, you start wading out away from the beach, the water gets progressively deeper, and then all of a sudden gets shallower. What happened is you're starting to walk on one of these longshore bars. Immediately before this longshore bar, we see a longshore trough. And this is where we have that slightly deeper water, and some of the sediment that's making that bar has come from that trough. So it's kind of been deepened and piled up right next to it. Here we see some more sand dunes as part of that back beach environment. You should be able to pick out the foreshore as well as kind of figure out where the nearshore environment is and the offshore. The offshore would be that dark blue area. The nearshore, we see all the breaking waves. The foreshore, sort of from the dunes all the way down to where the water line starts. Dunes, once again, be variable in size. It can be a couple centimeters in size, half a meter, all the way up to 10, 12, 15 meters in height, if not greater. Typically, on a healthy beach where you don't have a lot of erosion, you'll see that these dunes will be vegetated by grass or sometimes something called beach heather, or a few other different types of trees or plants. We can have sediment moving along a coastline either parallel to the coastline or perpendicular to the coastline. We're not going to focus too much on the perpendicular movement of sediment along a coastline. This we often see associated with rip currents. What we're going to look at more as parallel movement to the coastline. And to have movement of sediment parallel to the coastline, we need to have a shore parallel current. How do we create a shore parallel current? Well, what happens is you have waves approaching the shore, and the waves don't approach the shore straight on from like a 90-degree angle or perpendicular to the shoreline, but they approach at a angle. What happens then is that wave, and remember waves are really affected by what's going on in the bottom. If they can feel the bottom, they start to slow down. The bottom meaning the bottom of the sea floor, the waves will start to slow down. So when that wave starts to approach the shoreline at an angle, at one end, that wave is going to slow down faster and quicker than at the other end, because at one end of the wave, here would be on the left-hand side of the image, reaches shallower water faster than the other part of the wave. So this causes wave refraction, and what happens then as a result of this is we see that part of the wave's energy is directed perpendicular to the shoreline, and part of the energy that's being carried, transported by that wave, is directed parallel to the shoreline. That results in the creation or the generation of something called a longshore current that runs along the shoreline, paralleling the direction of the shoreline. So here's another look at what's happening. We can see in this overhead shot, we have the waves approaching the shoreline. This time it's the wave, the end of the wave on the right-hand side that hits shallower water first. The velocity decreases, the wave starts to bend, it starts to refract, and we generate the shore parallel current, something known as a longshore current. And as we'll see, these longshore currents are important because they're responsible for the movement of sediment up and down along a beach, as well as plays a role in erosion and deposition of material. If you're unsure that these shore parallel currents actually exist, consider this scenario. Imagine you go to the beach along the ocean to spend a nice sunny day with your friends. You're sitting in the water. You're going to be this sort of yellow, happy face. You're sitting in the water. You're not actively swimming. You're just kind of sitting there bobbing along on the waves, watching your friends sit there and lounge on the beach, getting a tan. And you kind of, things are happy. Things are going great. Look up at the sky. You continue to bob along. And what happens in a few minutes? Well, a few minutes later, you look up and you're no longer near your friends. You've actually moved down the beach some direction away from them. You're like, oh no, where'd they go? And you find out that it was you yourself that moved. And that's basically you've been caught up in that shore parallel current. There's a current, even though the waves are moving on shore, there's also a current that's moving you along parallel to the beach. So you can have waves operating, moving material on shore, and we can have that current moving material, a ball, sediment, parallel to the coastline as well. So as a result of wind waves refracting as they approach shallower water, these waves bending, we have this creation of this longshore current. We also have something else that occurs on the beach. Remember, not only is that current moving material parallel to the beach line, but we also have waves that run up and down the shoreline. Once again, these waves are moving in at an angle. So the wave moves on shore at an angle. What happens though is gravity takes over. So the wave moves up on the shoreline, reaches the highest point that's going to reach. That water is now going to return back into the ocean. It doesn't return back to the ocean at an angle, but it's going to return back to the ocean straight down, perpendicular to the beach. And this is because of gravity. Gravity is going to pull it down. It's going to take the shortest route down back to the water. So now we have this zigzag movement of water on the beach. Wave comes in, water moves up at an angle to the beach, and then it comes back out perpendicular to the beach. This is known as the movement of water up is known as the swash. The movement of water down is known as the backwash. If you're a little grain of sediment that's caught up in that wave and is moving with that water, with that wave as it washes onto shore, you're going to move up the shore at an angle and move down perpendicular. And what happens is we see the movement of sediment down a coastline, the movement of sand down the coastline in a zigzag path, and we call this longshore drift. So we move sediment along coastlines as a combination of both longshore current operating just offshore, as well as this longshore drift, the zigzag movement of sediment along the actual beach face. Another slide illustrating what happens with longshore drift, that zigzag motion of sediment along a beach. If you want to know more, if you don't completely understand the concept of longshore drift and longshore current, watch the video with a link there. As I said, this is really important when we start talking about different features that form on beaches or form along coastlines more accurately.